So oyster shear is a bulk waste, and globally, there's 17.5 million tons of oyster and similar species produced. And I think in China it's about 5 million tons every year. And currently, most of the oyster shear was piled on coast zone, and of course to produce public health concerns. It's because of its smell, and also it ejects some insects. So if we can use this waste material for some useful application, it will be nice. And when we talk about the shears, probably 10 to 15 years ago, there were a lot of research from chemists and material scientists. They focus on the nanostructure of sea shear. And of course, this material was produced by a natural process called biomineralization. And in terms of structure, the basic unit of the shear is interlaid hard materials, which is calcium carbonate, and soft materials, which is a protein. So this is from a science point of view, it's a very interesting material. And if we use oyster shear as an amendment for soil elimination, then we can reduce the use of limestone, because mining limestone is an environmentally unfriendly process. It destroys landscape, and limestone has to be heated around 900 to 1000 Celsius degree to produce lime. But for oyster shear, because of its nanostructure of calcium carbonate with protein, and as protein is a soft material, you can relatively easily destroy it. So for example, by heating to 600 Celsius degree, the protein will be gone, and creating a lot of micro space, and make it a final product, which is actually is calcium oxide, the porous material with adsorption properties. So the second part is how we did the work. As first, we collect oyster shear from local market, and of course dry it, crush it to small particles, 2 millimeters, and put it in an oven for heating at 800 Celsius degree for 4 hours, and the end product is crushed and sieved to less than 60 meshes. So this whole process from the oyster shear to calcite oyster shear is a relatively easy process of heating, and some details of the work has been mentioned in this publication, Bulletin of Environmental Contamination and Toxicology. So this is one of the raw material we use. And the second raw material is humic substance. So we buy some leonardite. As many of you would know, leonardite is a kind of a brown coal. It's a cheap coal because its heat intensity is very low. So normally you wouldn't use leonardite for burning, but this material is very abundant in China, in many parts of the world. So we use pulverized leonardite as a raw material and put it into 0.1 molar calcium hydroxide, and by shaking for a few hours, we can extract humic acid from this raw material. And then we combine the humic acid with the calcite oyster shear, and to produce the so-called oyster shear humic complex, So this black material is both organic component and inorganic component. Is really useful for absorption of heavy metals. And the details of these laboratory procedures have been reported in a publication last year. And in terms of the soil, we collected the soil sample from a place called Foshan City. It's near Hong Kong, so it's around here. And the topsoil, 20 centimeters, was collected, and it was analyzed in a laboratory for its physical chemical properties. So the soil had a pH of just over 6, a total cadmium concentration of over 5 ppm. So by national standard, if a soil has 0.5 milligram per kilogram of cadmium, it's contaminated. So this one is 10 times the threshold. And total arsenic is about 10 ppm. So both cadmium and arsenic are termed as so-called heavy metals. And they are two of the most trouble heavy metals because of their high toxicity and the carcinogenic nature of these elements, and also because of their opposite chemical behavior. It's really hard to deal with both cadmium and arsenic in soil at the same time. So the next part is we did a pot experiment. We mixed the contaminated soil with soil amendment, or as the shear humic complex. And this complex was added to soil at a different dosage. This is a control with 0% to 0.5, 1%, 2%, up to 5%. As you can see from the figure, if you add too much of the amendment, it will affect the plant growth. Here the plant is a commonly consumed vegetable called bok choy. It's a really popular vegetable. So if we add too much, of course, not good, because the amendment has a very high pH and it will destroy the suitable environment for plant growth. But up to 2%, it will be fine. So this pot experiment is to assess the effect of this oyster shear humic complex on the uptake of the toxic metals, cadmium and arsenic by plant. And the next part of the work is we assume a child is playing in the field and sometimes put his fingers into his mouth, and you could introduce soil into your body. So in these cases, there's a process to assess the effect of ingested soil, how this ingested soil would potentially causes human health risk. So this is a unified bioaccessibility method developed in the European countries is adopted to show if we add this soil amendment to contaminated soil, how could say human health risk of cadmium and arsenic be reduced. And this assessment involves the preparing of the simulated stomach solution and simulated intestinal solution, and put the soil into the solution and shake for a while, and then centrifuge filter, analyze the solution, determine the metal concentrations, and then based on a formula we calculated the bioaccessibility index. So this is the results and discussion. First, what the calcite oyster shear looks like. So on the left side, it was before heating. Oyster shear in its original state. You can see the layered structure of the material. And on the right side is after 800 Celsius degree calculation. So the end product is like a cubic material. And by X-ray difflection analysis, we will determine the mineralogical compositions of the product. So the oil shear before heating, heating at 400, 500, 600, 700, 800 Celsius degrees. So as the temperature increase, the original composition, which is calcium carbonate, gradually disappear. And the end product is calcium oxide. So after 4 hours of heating at 800 Celsius degree, it is enough to convert calcium carbonate into calcium oxide. So this table shows the chemical and physical properties. So the oil shear before heating had a pH close to 9. After heating, the pH increased a lot, 12.75. And the specific surface area slightly increased. And this material itself is cadmium and arsenic content. Of course, we have to determine it to make sure the material itself is safer to be added into soil. So their concentration are way below the national guideline limit. So the material itself could be used in soil. And in terms of the complex, the oil shear humic complex, and of course this material has an inorganic component, which is as shown in the ash content, and organic compound characterized by the high carbon content, 30%, oxygen content, some nitrogen and sulfur. But more important to my work is called the functional groups of this material. So particularly we determined phenolic hydroxyl group and a carboxyl group of the material. And the value is really, really large. So these function groups are useful in combining arsenic and cadmium to form stable complex. So this is behind this adsorption capacity. And of course, this material itself is low in the toxic cadmium and arsenic content, so that it meets the requirement be used as a soil amendment. So in the pot experiment, we use the vegetable bok choy and add the complex as a soil amendment. So it's a different dosage from 0 to 5%. And of course, after adding this really alkaline material, the pH increase with the dosage, but still within the range the plant can tolerate. And as a biomass, because only the above ground portion of the vegetable is consumable, so we determine the above ground biomass. So the biomass remains relatively stable until you add too much of the amendment, the 5%. And the toxic cadmium and arsenic content in the vegetable is reduced when the dosage increased to 2%. So specifically, by adding 2% of the amendment, we can reduce the toxic metal concentration below or close to the national food safety standard. So the cadmium is for 0.05 ppm, arsenic is 0.5 ppm. So the soil before remediation, it can grow vegetable, but as a product does not meet the safety requirement. And after adding soil amendment, we can get the value close to the safety standard. And the next part is on the bioaccessibility test. So assume some children take soils in, and what kind of effect, what kind of risk what the soil has on their health. So again, we add amendment into soil. It's a different dosage. And then use the gastric or intestinal simulation solution and add the soil to in the simulation solution and extract how much of the cadmium and arsenic could be dissolved. Probably I typed along here. It's, one is here, one is gastric, one is intestinal. So anyway, is the amendment dosage increased, so by accessibility of both cadmium and arsenic reduced dramatically. So which shows that in the contaminated soil, if we add this oyster shear humic complex amendment, then we can reduce the risk of the soil on human health. And here shows what kind of advantages we have by using oyster shear humic complex for soil remediation in comparison with calcite oyster shear itself. Because about 10 years ago, some research work started on using calcite oyster shear. But the problem is oyster shear is that after calcination, it has a really high pH, somewhere between 12 and 13, because its main composition is lime. So the really high pH is not safe for handling. If accidentally the lime get into your eye, it will damage your eyesight. So by adding humic substance to the calcite oyster shear, we can reduce the pH, so makes the complex safer to use. And the second advantage is the humic component of the complex provide abundant functional groups, particularly carboxyl groups and hydroxyl groups for the absorption of cadmium and arsenic. So the complex providing better capacity for retaining the metal in soil and preventing them being absorbed by, uptake by a vegetable. And third advantage is that this complex could remain in soil longer than calcite shear alone, because calcium oxide, after it's reacted with water, it's become soluble. But the complex is quite stable because of the protection of humic acid on the calcium oxide. And here's a brief conclusions and perspectives. So from this work, we can show that oyster shear humic complex is an effective amendment for the remediation of both cadmium and arsenic contaminated soil. So this cadmium and arsenic contaminated soil is a common problem in the world, and particularly in some Asian countries, is a really serious problem. And cost-effective technology is much required for remediation of these kind of soils. And the second point is converting oyster shear to soil amendment will enhance the sustainability of aquaculture in coastal zone, because the accumulation of oyster shear waste is a problem, and we can, by solving this waste problem, we indirectly help the aquaculture activity. And the third part is probably the more theoretical one. In the natural environment, particularly in the tropical and subtropical area, because of much of the rainfall, high temperature, so rock weathering is faster, and the cation reaching from the soil, from the rock is severe, so that naturally the soil in tropical region is poor in fertility, it's acidic, because the calcium is lost. So by this work, if we put the oyster shear back into soil, we actually bring calcium back into soil. So this human activity, how this human activity could have on the whole ecological consequence, because the calcium migration from land to ocean has been partially reversed. So this is a theoretical question we would keep an eye on long term. Thank you very much for your attention. And here's my email address in case you need to contact me in the future. And in the next few minutes, I will welcome questions from you. Thank you.
Thank you so much, sir. Thank you so much for your wonderful presentation on the cell-humic complex for soil remediation. It was a wonderful presentation, and I'll leave some time here. If anyone have any questions or comments, you can please ask Professor Yuan.
Hello, good evening or good afternoon, Dr. Yuan.
Yeah,
I think it's really a good topics because in our laboratory we also doing some refrigeration system development for the oysters. So
okay.
I have I have maybe question about this is like as you know, oyster these days is a lot of them are farmed, not like the raw oyster as before. So did you did some study about? Did you have some like the perspective to see the different composition we will get from the farmed oyster and the maybe the from the raw oyster shells if we do this type of the analysis?
Okay.
To reduce the CD and the AS, which is good for like the human like health.
Okay. Yeah. Oyster shell, chemically speaking, its composition is about 96% of calcium carbonate and 3 or 4% of protein. So the composition is relatively stable with the same species, whether it's farmed or natural. And in China, particularly in the coastal area, most of oyster shell are farmed. So in the intersection of fresh water with seawater, this is the environment for oysters to grow.
Mm.
So for use its oyster shell waste as a material for soil remediation, probably it doesn't matter whether it's from natural growing or farmed oyster.
Okay, thank you.
Okay.